Hi everybody. It's been a few weeks now since we last had a look at our electronic DC load project, mainly due to other commitments I've had over the last few weeks. But I finally got round to having a look at some further updates to this project and making some more improvements to it, and that's what we're going to cover today. So just quickly recap on what we're going to do today, and then we'll look at it in more detail. Well, the first thing I had a look at was the power Mosfets and the way we have them paralleled up to give us the extra power capabilities. And there is some issues regarding heat on that particular arrangement. Certainly as you start drawing more power at the higher current ratings, there is a possibility that the one of the Mosfets could go into thermal runaway and break down. So we're going to have a look at how we can improve that particular part of the circuit. The second thing we're going to have a look at is I've had a lot of requests if we could have a user-defined battery cutoff voltage set by the user, and I've added that also as a new feature, mainly by changing some of the software. As I also did with the next item here, which is setting the safety limits. That's for the maximum power, maximum current and maximum temperature on the heatsink. So I've given that as a user-defined option as well. And we're going to also add a new option to the DC load, and that is the Transient Mode option, and I'll cover that in more detail shortly. I did look very closely at the software. I found one or two little issues with it. Certainly things like when you're using the keypad to input the settings, I found that things like the decimal point could be inputted twice, and just little things like that I've corrected. And then finally, as I promised last time, I'll just cover some of the alternative Mosfets that I found that you can also use in this project. Just go through a list of those that may be suitable for this project in place of the one that I've chosen. So let's have a look at these now in a little bit more detail. Now you may recall from our previous arrangement we had our power Mosfets all wired up in parallel as shown in this diagram here. So we had all the drains joined together, all the sources joined together. The gates were fed from the same drive voltage, but we had separate 100 ohm resistors feeding each of the gates to prevent parasitic oscillation, and that worked quite well. Now this method of paralleling power Mosfets relies on the fact that the Mosfet has a positive temperature coefficient with regard to the on resistance. And that has some form of balancing. If any one particular Mosfet tries to conduct more current than the others, then it gets hotter. As that Mosfet then gets hotter, the internal on resistance of that Mosfet increases, which then tends to counteract that. As the resistance increases, you get slightly less current flowing through it, so in theory it should cool down. So you get some form of self-balancing with these four Mosfets. Now I found in practice that this particular arrangement works quite well, certainly at currents of 1 amp or below on the DC load, but I found also now that as you're increasing the current through the load, say to 2 and 3 amps or more, then other factors come into play. And one of the other factors that comes into play is the fact that the gate source temperature coefficient of a Mosfet is actually negative. So we have a negative temperature coefficient on the gate source voltage of a Mosfet compared to a positive temperature coefficient of the on resistance of the Mosfet. So one would appear to counteract the other. Now the effect of the negative temperature coefficient of the gate source voltage on the Mosfet as the temperature rises is that as the temperature increases, you need less voltage on the gate to drive it to the same degree. But if you maintain the same voltage on that Mosfet, say there to the other three, when that situation occurs, then it drives it even harder. And as you drive the Mosfet even harder, then it gets even hotter. So you've got a cycle then starts to develop there. It goes into thermal runaway because as it gets hotter, the negative temperature coefficient of the gate source voltage then means we should have a lower voltage there at the gate, but we've maintained it at the higher voltage, so it's driven even harder, so the Mosfet then gets even hotter and we go into what we call thermal runaway. So that then simply hogs all the current, taking it away from the other three Mosfets here. So we need to have some arrangement to prevent that situation happening as we start drawing more current through the Mosfet. So we're going to have a look at how we can try and correct for that. But before we do that, I just want to have a look at some of the characteristics from the data sheet, just illustrating the points of the on resistance for the Mosfet and the gate source negative temperature coefficient as well. Just let's have a look at the data sheet for that. Here we now see two of the graphs I've taken from the data sheet for this power Mosfet that we're using. The one here on the left is what we explained before, which is the positive temperature coefficient of the on resistance. So as the temperature increases on the bottom scale there, the on resistance also increases in a positive direction. So that's a positive temperature coefficient. And this factor here down the left hand side is what you multiply the on resistance of this power Mosfet with to get the true resistance, the true on resistance. And if we look at the data sheet, we can see that this particular power Mosfet normally has a maximum on resistance of around 6 milliohms, and therefore if we increase the temperature to something like 120 degrees C, then if we plot across here we get a factor there of, I think it's 2.2. So you have to multiply the 6 milliohms with a factor of 2.2. So it more than doubles the value of the on resistance of the Mosfet. So you can see that effect there quite clearly. As the temperature goes down, say to 60 degrees, then you're only going to multiply it by a factor of just over 1.2. Now on the right hand side here, this is the graph that illustrates the effect of the gate source threshold voltage as a function of the junction temperature. So as the junction temperature of the Mosfet increases, here you see we have a negative temperature coefficient going down. So if we take the typical line there, the dotted line in the middle, if we look at a temperature of say 60 degrees centigrade, then you can see here that we need a threshold voltage of 1.5 volts to conduct the current flow through the Mosfet, whereas when we increase the temperature to around 120 degrees centigrade, you only need about 1 volt. So you can clearly see here that as the temperature increases, we require less gate source voltage to drive it to the same degree. But if we were to maintain the same source voltage, gate source voltage, even though it's getting hotter, you drive it harder, and that's what would cause it to go into a thermal runaway situation. So these two graphs illustrate the 2 points that I just covered earlier. So let's have a look at how we can overcome this effect with our circuit today, and with some changes that we're going to make to the wiring arrangement and the layout arrangement for that matter of the power Mosfets. Right, well here you see now the new arrangement I have for the wiring of the power Mosfets, and straight away you'll notice that we've added an additional resistor in the source returns of each of the Mosfets. But before I come on to that, I just want to mention about the arrangement of these Mosfets on the heatsink, the positioning on the heatsink. That's also important. If you recall, previously we had the Mosfets all staggered across the heatsink, which seemed to be a good idea at the time, but if you want to maintain the same temperature in each of the Mosfets to ensure that you equalize the current flow in through them, then the best way to do that is to position the 4 power Mosfets as close as possible together. And you can see here, this is the arrangement I've used today. I've mounted them in a square butting up to each other, so they're as close to each other as possible. And that means that if any one of these Mosfets starts to conduct more current than the other and gets hotter, the hottest one will then transfer some of that heat to the other 3, and thereby the other 3 would also increase in temperature, and that will also then have an effect to counteract the one that was getting hot in the first place. So it's important to position the Mosfets as closely together as possible. That's what I've done. I've also taken off the mica washer. As we're only operating these at around 30 volts DC load, then we can quite safely mount these Mosfets directly onto the heatsink without any mica washer, and you get a better heat transfer. So that's the first thing I've done, mounted the Mosfets as close as possible together. Then what we've done is we've added, as I say, an additional 0.1 ohm resistor in series with the source of each Mosfet, and they're all then joined up and going through the current sense resistor there, that 0.1 ohm resistor there. Now the voltage for the gate source, the drive there, is now going from the gate via the 100 ohm resistors to the bottom end of these 0.1s. So what you can see now is that if any one of these Mosfets starts to draw more current than any of the other three, then you'll get a bigger voltage drop across one of these 0.1 ohm resistors. And what that will do is effectively then start to reduce the gate source voltage of a particular Mosfet compared to the other three. And that in effect will then reduce the current flow through that Mosfet, bringing it back into balance again. So by simply adding these four resistors, it has the effect of balancing out the negative temperature coefficient of the gate source voltage of the Mosfets, which will tend to cause it to get hotter. So that's what we've done today, and I've tested that and it seems to work quite well in combination with positioning the Mosfets as closely as possible together. And I'll show you that on the actual heatsink of how I've arranged that. Now the wattage of these resistors doesn't have to be as large as the 0.1 here, because you'll only have around a quarter of the power going through any one of these as we have with that. So you can probably get away with a 2 or 3 watt resistor at the most in these locations here, and that's what I've done. So let's have a look at the arrangement of that on the heatsink. Here we now see the new arrangement for the Mosfets on the heatsink. As you clearly can see there, the 4 Mosfets are bolted closely together in a little square in that location there. The 0.1 ohm sense resistor is mounted on the heatsink in that position now there, and the temperature sensor IC is now mounted in that position just there. And you can clearly now see there we have the 4 100 ohm gate resistors, then joined together. The yellow wire then is going to the gate drive on the main PCB, and these resistors you can now see are those additional 0.1 ohm resistors I've put in series with the source of each of the Mosfets. And what I've been careful to do is make sure that when I've soldered these 0.1 ohm resistors onto the source of the Mosfets, I've kept all of the leads of the resistors the same length. So I didn't cut them down, I kept them all exactly the same length. And in fact I've used here, I think these are 5 watt little wire wound resistors, but you can actually use probably 2 or 3 watt resistors. You don't need to have it as large as what I've got here. One important thing you need to bear in mind is that they need to be reasonably good quality, at least 5% tolerance, and the ones I've chosen here, as you can see, are 5% tolerance. So that's the arrangement, the new arrangement now on the heatsink. And the other thing I've done on the heatsink, I've mounted a fan directly behind these on the other side of the heatsink, and for that I'm using a slightly larger fan than we used previously. I managed to salvage one from a computer cabinet fan, and that works quite well. I'll show you that. There we see on the reverse side of the heatsink, they have got that fan mounted on there, which is just simply then blowing cold air onto the back of the heatsink directly behind the 4 Mosfets, and a slightly bigger fan to what we used previously. Now before we move away from looking at the heatsink, I just want to point out that the temperature sensor IC there still does require a mica washer to insulate it from the heatsink, otherwise you'd have some issues. Whereas all the 4 power Mosfets are now bolted directly onto the heatsink without a mica washer, but using heatsink compound. Right, well I now just want to demonstrate the effect of those 0.1 ohm resistors in the source return of each of the power MOSFETs. So what I've done here is I've connected a voltmeter across each of those 0.1 ohm resistors so we can monitor effectively the current flowing through each of the MOSFETs. And what I'm going to do is switch the load on. I've set the load to 1 amp. So if I switch the load on, we can now monitor the voltage across each of those resistors, and you can clearly see we have a difference of, there's 24 millivolts, 28, 22, 24, which means you can clearly see that this one here at 28 millivolts, to generate a higher voltage there, we've got more current flowing through that particular MOSFET. If I increase the current up to 2 amps, and again you can clearly see now that we've got 48 millivolts, 54, 45, 48. So clearly again this particular MOSFET we're monitoring here with 54 millivolts is drawing the most current. So what we're going to do now is show you the actual gate source voltage of each MOSFET, because this voltage difference here will subtract from that and give us some form of balancing. Now measuring the voltage between the gate and source of each of the MOSFETs. So these are the actual readings here. I've got it set at the moment to 1 amp. So you can see here that the gate source voltage is pretty close to one another. You've got 1.98, 1.98, 1.98, 1.98. So you can see how they're fairly well balanced out. If I increase the current to say 2 amps, increasing it 2 amps, we've got 2.025, 2.018, 2.028, 2.020. Again, fairly closely related to each other there. So you get some form of balancing there, and as the one that's drawing the most current heats up and heats up the other three, then that balancing of that voltage and current flow through the MOSFETs will improve. The next thing I'm going to do is just have a look with my thermal camera at the heat radiating from those 4 power MOSFETs. So I'm going to just position my thermal camera on them if I can and switch the power on. So I've got the load on, running at 2 amps. What I'll do is I'll zoom into the thermal camera and you can have a look. I think there you can now see the heat radiating from those MOSFETs, and it looks as though we've got a fairly even spread of heat around the 4 MOSFETs. So I'm quite happy with that. The next thing we're going to do is have a look at some of the changes I've made, and these particularly with the software for zeroing the reading when you first switch on, and also for user-defined safety limits. So let me just switch the unit on. As you can see there, I'm now on version 24 of the software, and at the moment you can see that the readings are not exactly zero, and if you remember before we used to zero those out with the 0 button, but I'm using that digital pin now for the new transient mode. So I've now altered the software such that if you press the hash button and press the rotary encoder button in at the same time, it will zero the reading. So the supply voltage is off at the moment, so if I press the hash and the button here at the same time, and you can see there that we've now zeroed the reading. So that's the first change that I made there with the setup. The next new feature we've added on the DC load is the ability for the user to change the safety modes. That means you can set the maximum current, the maximum allowed power, and the maximum allowed temperature on the heatsink. And again we use a combination of a 2 button press for that, using the rotary encoder switch button by pressing that in, and at the same time pressing in the star button there. So let's do that. Once you're in the user setup mode, the first thing it asks you for is the current limit. The default setting at the moment is set at 5 amps, but let's say you want to set it at 3. If you want a decimal place, you press the star button, 0.1. If you weren't happy with that setting before you enter it, you can press the C button to clear that, so we can clear that and put a new value in. Let's say it's 3.2 amp, and then you press the hash button to enter that. The next thing it asks you for the power limit in watts. The default setting at the moment is 50 watts, but we can change that to say 20 watts to 0. Again, if you weren't happy with that, you could press the C button to clear that and put a new one. Let's say I want 21.5. Again, press the hash button to enter that. And then the final thing is to set the temperature, and we can set that to say 35 degrees C and press enter. And all of those settings will be used in the DC load from now on until you switch the load off. At the moment it's not stored in EEPROM, so when you do reset the DC load it reverts back to the default settings. But it's something we can change in software later, where we can store those in EEPROM if we wish. Having done that, it then reverts back to the constant current mode, which is the default mode at startup. Now the other new feature is the ability for the user to define the battery cutoff voltage in the battery capacity mode. So we'll demonstrate that next. If you remember, to go into that mode we press the D button on the keypad. That takes you into the battery capacity mode. Let me do that. And this time what you'll see is we've got another option. So we've got all the options we had before, LiPo, Li-Fi, NiCad, zinc, and now we have a 5, which is the set voltage, and 6 is exit. If you want to exit out of this and go back to constant current. So by pressing the 5 button it allows you to set your own cutoff voltage. So if we press 5, it then says enter the battery cutoff voltage, and again you use that use the keypad to enter the cutoff voltage. So if we enter a cutoff voltage of say 3, use the star for the decimal point, 6 volts if that's what you wanted. Again, if you weren't happy with that, if you press the C button it'll clear that reading and allow you to put in a different reading. So let's put it at 3.5 volts, and then to enter that you press the hash key. Press the hash, so it now tells you we've set the cutoff voltage for 3.5. We can now set the current to 1 amp. At the moment 1 amp, and the reading at the moment is 4.294 volts. So let's switch the load on. So it will now start discharging the battery and calculating the milliampere hours. At the moment I'm simulating that on a power supply, but if I now gradually take the voltage down, and you'll notice now when it gets to that 3.5 volts it should cut off. So let's so 3.6, 3.57, and then we're going below 3.5 and it then cuts off. So that's a nice little useful feature there, which allows you then to set your own cutoff voltage in addition to the pre-set ones that we've already got there as we had before. The new mode we've added is this transient mode, and just quickly review that. We have 3 options. We have a continuous, we have a toggle, and we have a pulse. If we look at the continuous transient mode first of all, we simply set a high and low current, and you set a time in milliseconds. What happens then is that once you switch the load on, the transient mode comes into operation and switches between the high and low currents at the time period that you set in milliseconds. So if we set the time period to 100 milliseconds, it'll be high for 100 milliseconds, low for 100 milliseconds. So it's symmetrical, the waveform coming out, and that is continuous as long as the load is on. The next option we have is the toggle mode. Again, you set a high and low current, but this time you don't need to set a time, because the transient between the two is going to be activated by a trigger pulse. When it receives the first trigger pulse, it goes high. When it receives the next trigger pulse, it goes low. So every time it receives a trigger pulse, it will toggle between the high and low current settings. The last mode is the pulse option. Again, we set a high and low current, and also this time we set a time period, but the time period this time is only used to give the duration of the high current once we receive a trigger. So on the first trigger pulse, it goes from low to high, and it then stays high for the time period and then immediately goes low. It will then stay low until it receives the next trigger pulse, and on the next trigger pulse it will go high again and then stay high for that time period. So you can have a situation where, let's say, it goes high for 100 milliseconds, and then you can be down here in the low current setting for a second or more until it receives the next trigger pulse. It then goes high again for 100 milliseconds and then goes low. So they're the three options that we have in our transient mode, and we'll have a look at that on the DC load. Just quickly before we go to have a look at the actual transient mode on the DC load, I just want to point out that we're using analog pin A2 as a digital pin for the trigger input pulse. Previously that pin was being used for the 0 button, and as I mentioned earlier, we now have a new arrangement for the 0 button. So that's freed that pin up there for the transient trigger pulse, and it's configured in such a way where it's currently held high, and so when it receives a negative trigger pulse, it then activates the transient mode. So I'm showing here trigger pulses. So on that leading edge there, the negative leading edge there, it supplies the trigger for the transient mode. Now I'll be demonstrating this simply using a push button to ground for the purpose of today, but at a later stage I think I'll make a little pulse shaping circuit which will allow us to input a positive pulse as the trigger pulse by having some inversion there, probably a Schmidt trigger inverter, and I may even decide to reduce the width of the pulse by using a differentiator, a capacitor and a resistor as a differentiator to give us a narrower pulse. But we'll have a look at a pulse shaping circuit maybe later, but for today I just want to demonstrate the transient mode by simply putting a negative pulse onto A2 there, and I'll be doing that simply with a little push button to ground. We'll just now demonstrate the transient mode, and to go into the transient mode, again it's a 2-button press to get into that mode. This time we're going to press the rotary encoder button in, and at the same time press the A button. So pressing those 2 buttons at the same time takes you into transient mode, and now we have 4 options here. The 4th option is exit to go back to constant current, the default setting. And the other 3 options is, 1 is the continuous transient pulse, 2 is a toggle pulse, and 3 is the pulse, the triggered pulse. So let me just demonstrate the first one, which is the continuous one, by pressing number 1. And the first thing it asks you to do is set the low current. So if we set the low current to say 1 amp, so we press 1. If we want a decimal point, we can put 0.2. If you make a mistake there, again pressing the C button would clear that, and you could put in a new low current. Let's just put in a 1. If we just put in 1 on its own and press the hash button, it'll use 1 amp. It then asks you for set the high current. Let's set the high current to, if I put 2, again if you use a star, 2.2. If you weren't happy with that, again pressing the C clears that, so you can put in say just 2 amp. Press the hash button to enter that, and then set the time in milliseconds. Let's set that so we can see it. Let's set it at 2000 milliseconds. That's 2 seconds to 2000 milliseconds, and then pressing the hash button enters all of that in, and as you see there now, the display is DC load is off. The low current is set at 1 amp, the high current is 2 amp, and the time is 2000 milliseconds. So I'm now, and we can monitor the current there and the voltage. It's at 3 volts at the moment. Let's just step the voltage up to say something around 12, just over 12 and a half volts, say. And now we've got the current set there, high and low. So now pressing the load button, so the load is on. And what you'll notice here now is that the current is switching between 1 and 2 amps. If you look at that, every 2 seconds there. Switching the load off, and then to get out of that mode you can then press any of the other mode buttons, A to D. Let's press A, goes back into constant current mode. And if I want to go back into transient mode again, let's press the A and this time I'm going to use the toggle mode. That's 2, so pressing 2. Again, it asks you for the low current, which let's put in 0.5 of an amp, and the high current, let's set that at 2 amp. But this time you notice it didn't ask us for a time, because it's now going to toggle on a trigger pulse. The load is off at the moment. If I switch the load on, because we have no trigger pulse at the moment, we've got no current. If I supply a trigger, and the first trigger pulse has gone to 0.5 of an amp, next trigger pulse goes to 2 amp, next trigger pulse goes back to, next trigger pulse goes back to 0.5. So it just toggles between the two now by every trigger pulse. I'm just simulating a trigger pulse with a push button at the moment, which is not ideal, but it just illustrates the point, just toggling between the two. So that's the toggle mode. Again, to come out of that mode, just press the A button. Now we're going to go back into the transient mode again, and this time I'm going to select the pulse mode, number 3. So I'm going to select the low current to 1 amp, high current to 2 amp, and now this time we do need to put in a time, so let's put a time in, say, of 1000 milliseconds. It's 1 second, and then press the hash to enter that. So now you can see there we've got low current 1 amp, high current 2 amp, 1000 millisecond time. The load is off at the moment, so let me put the load on, and at the moment you can see it's running at the low current 1 amp. If I now supply a trigger pulse, it goes to 2 amp, but only for a second, and then goes back to 1 amp. So supply a trigger pulse, goes to 2 amp for a second, and then goes back to the low setting. So that's on the pulse mode. Return back to constant current with pressing the A. So there we have the different options of the transient mode. As promised, I thought we'd just have a quick look at the alternative power MOSFETs we could use for this project. The favoured one I'm using at the moment is the one by NXP, the BUK 956R1-100. That has good specification. These are headline figures from the datasheet. 100 volt maximum drain source voltage, maximum power rating is 349 watts, and the on resistance is 6.1 milliohms. So that's the favoured MOSFET. If you can't get hold of that one, then there's one by ST Microelectronics, which is the STP80NF55-06. Very similar in terms of headline specification there, apart from the voltage is down at about half, at 55 volts. It shouldn't cause a problem because, as we set out with this DC load, we said we're aiming at a 30 volt load maximum, so at 30 volt load that will still be suitable. The power rating is slightly lower, but the on resistance is very similar, so that will be a suitable alternative. In addition to those two, there's a couple here which are not quite as good, but you could use them. Again, the voltage, the maximum voltage rating is around half of the 100 volt one there, but the first one there, another NXP, the power rating is very similar, and in fact the on resistance of that one is much lower, 2.6 milliohms. And finally, there's one by International Rectifiers which could still work, but you'll notice here that the absolute maximum power rating is 170 watts, and also the on resistance is much higher, so this one will probably run much hotter. So if I was choosing, it would be a choice of one of the top three that would be suitable for this particular project. All of these Mosfets are logic level gate driven, so they're all suitable in terms of driving it with that gate voltage. The only thing I would mention is that these are absolute maximum ratings here, so you'll never achieve these power rated wattage figures here when it's actually operating. These are specified at 25 degrees centigrade or ambient temperature. In reality, when the DC load is operating and the Mosfets are getting hot, you'll be running at probably half or less than half of this maximum power rating possibility here. But even having said that, we did say that we're looking at our power rating maximum of around 99 watts. We set the initial maximum at the moment in software at 50 watts. So again, all of these would be suitable for the project. So there we are. There's the alternatives which you can try if you have trouble getting the first one there on the list.
Finally, I just want to point out one or two things regarding the keypad entry and clearing the entry if you make a mistake. You'll have noticed that when I was using the battery capacity mode, which is the D button there, or I was using the transient mode or doing the setup procedure, if I make a mistake in entering the data via the keypad, then we can simply press the C button to clear that and retype again. However, if you're in the normal function mode, the basic operation, which is constant current, which is the A button, constant power B, and constant resistance C, then to clear an incorrect entry, in those cases you simply press the function button again. So if I give you an example of that, if we type in 1.7, rather than press the hash key to enter that, say we made a mistake there, to clear that we simply press the A button again, which is the constant current button. It clears that and you can add in the new entry 1.2 and press the hash key. And the same applies if you're going on constant power, which is the B button. If you make a mistake when you enter the number, which is echoed there at the bottom, simply pressing the B button again in constant power clears that and you can enter the new number and press hash again. And the same applies with the constant resistance. Make a mistake where it's echoed at the bottom there, simply pressing the C button again clears that and you can put in a new value. Now the other thing I'll point out is in the bottom right hand corner of the display you've got the indication of which mode you're in. In this case it's CC, which is constant current, and those two letters will change depending on what mode you're in. So if you go to constant power it's CP, constant resistance it's CR, and battery capacity, when you go into the mode it shows it as BC. When you then go into the transient mode, depending on which one you select, if you select one which is continuous and you enter the current settings and the time period. Then once it goes into that mode there, you'll see at the bottom right hand corner again you've got TC, which is transient continuous, and if you go into the other transient modes you'll either see TT for the toggle mode or TP for the pulse mode.
Well, I think I'm going to leave the project there for today. I hope you found the additions and the changes I've made of interest. What I will do is I'll put some links down below where you can download the latest version of the software, and I'll make the changes to the schematic as well and give you that as a new link too. Now, as we've added a lot of new features to this project, I thought it might be useful to get the time to put together a user guide for it. So if I do finish the user guide, what I will do is I'll add that as a link later as well below. Now, as far as finalising this project, I'll have a look a little bit later about the trigger input circuitry there with some pulse shaping and finalise that. And we could have a look at just adding an extra feature on the transient mode. One is a list mode, if I get the time to have a look at that, and tidying up any other issues that we have. So maybe next time we can just finalise the whole project, but for now I'm going to say cheerio. Please give me a thumbs up and subscribe, and I'll see you all again soon next time. Bye for now.